Okay guys, last new stuff for four-sided units are the kites and the trapezoids. They have their own special little set of rules. They're different from parallelograms in that they don't have two pairs of parallel sides. So we'll start with the kite. It looks kind of like what we think of as something you fly on the beach. A kite is a quadrilateral, which means it has to have four sides, with two pairs of congruent adjacent sides. For parallelograms, including the special cases like rhombuses and rectangles and squares, it's always the opposite sides that are congruent. For a kite, it's the next door neighbors. So we have a kite in this picture that already has the diagonals drawn in. The kite is just the outer four sides. We have two congruent sides up at the top, two congruent sides going down toward the bottom. If we ignore these diagonals at first, that we can kind of take a look at the angles. It turns out that the angle formed by the pair of shorter sides is a fairly good sized angle. That looks like it's almost a right angle. The angle formed by the longer sides is a little pointier, so that one's definitely smaller. It's an acute angle. So the angles on those opposite corners are not the same, which was true for a parallelogram. So the angles formed by the congruent adjacent sides are not equal angles. But if you think about this long diagonal going from the top to the bottom, it divides the picture into two equal pieces, this left half and right half. They are mirror images of each other, which means that this leftmost angle here and the rightmost angle over here of the big kite, those are congruent. So let's jot down some properties. The angles formed by two non-congruent sides are congruent. They're the same. The other two are not. So one pair of congruent opposite angles. Another thing that's true is the angle at which the two diagonals cross is a special case. The vertical diagonal and the horizontal diagonal, they're perpendicular lines, so they actually form four right angles in the center of the figure. So property number 2 is that diagonals are perpendicular. Fancy word for makes right angles. All four of those angles are 90. And those are the two biggies. Other things that are true that we're not going to bother to write down because they get a little more complicated to try to write out in words. The top two triangles, those are congruent by angle side. Actually, we're hypotenuse leg. We can use a hypotenuse leg there. The bottom two triangles, those are also congruent by the hypotenuse leg theorem. If you just take a close look at the picture, it's obvious that these two triangles they're the same. These two triangles look to be the same, which means if you know this top angle is 30 degrees, you're going to know for sure this top half is 30 degrees. So we're going to bisect that angle up there. These bottom two pieces, those are equal. These two parts of angles here and here, those are not going to be the same. One of those is going to be smaller than the other one every single time. If they were equal, we would end up having a rhombus instead of a kite. Okay. Trapezoids. A trapezoid is a quadrilateral with exactly one pair of parallel sides. The picture below is a trapezoid. Let's say the top and the bottom sides are the two parallel sides. So we're going to mark those with parallel marks. Those are called the bases. So let's just label those. The top is a base, the bottom is a base. It doesn't matter which one is which. Sometimes we'll label one B with a 1 as a subscript, and we'll label the other one B with a 2 as a subscript. Doesn't really matter which one's which. The other two sides, the ones that are not parallel, those are called the legs. So every trapezoid has two bases and two legs, and the bases are always the parallel sides. The two angles up at the top base are considered one pair of base angles. The two angles at the bottom base are considered another pair of base angles. Okay? Because the trapezoid can take on so many different types of looks, there's never any guarantee that the diagonals are the same size. As a matter of fact, this diagonal from top left to bottom right is longer than the diagonal from the top right to the bottom left. They don't cut each other in half. They don't operate anything like the parallelogram rules do. There is one thing for sure that's always true about these, and that's that two angles along the same leg are supplementary. Which is that fancy word for they add up to 180 degrees. There's no guarantee that any two sides are the same length. They can all four be different. The bases can never be the same, because if the bases were the same, we'd have a parallelogram. But the angles, there's always this supplementary relationship. So if the top angle were, let's say, 89 degrees, top left angle, then the bottom left, which is along the same leg, the left leg, would have to be supplementary. So 180 minus 89 is 91 degrees. Those add up to 180. If the bottom right hand angle were 80 degrees, then the top right we could get by subtracting 80 from 180, so that one would be 100 degrees. There is no necessary relationship between anything in opposite corners. There's no necessary relationship between two angles that are at the same base. They never have a particular predictable relationship. The only relationship that's predictable is at the same leg that add up to 180. And it's because of those parallel line rules we learned in Chapter 3 that govern how those same side interior angles are related. However, one thing that is true about trapezoids is they have mid-segments, and mid-segments do something that's very predictable. If you take a trapezoid, two parallel sides, with a leg on the left, a leg on the right, and we take the midpoint of the left leg, so eyeball kind of where you think the middle is, maybe kind of down here, that piece is equal to that piece, and eyeball the midpoint of the right side, that piece is equal to that piece, and then connect the dots. That makes a mid-segment. It's very much like the mid-segment of a triangle, which is also a line segment that connects two midpoints. Okay, the first thing that's true about a mid-segment is that it's parallel to the bases. So property number one is that it's parallel to the bases. And I'm going to abbreviate and use the symbol for parallel instead of the word just to save a little bit of time. The other thing that's true is the length is predictable. Well, let me throw out some numbers. If the top were 10 inches long and the bottom were 20 inches long, how long do you predict the middle would be, this mid-segment? So if you guess 15, you know what you're talking about. We want to know what's halfway between 10 and 20, because the length of the mid-segment is halfway between the lengths of the two bases. Another way to say that is it's the average of the two. So the length of the mid-segment is the average of the bases. So if we take 10 plus 20, add them up, and divide by 2, that's how we find an average. 10 plus 20 is 30. 30 divided by 2 is 15. So the mid-segment is 15 inches. Sometimes you can just know what the middle number is. You kind of do it in your head. If the numbers get uglier, then just average the two. Pick up a calculator and crunch the numbers if they get bad. So parallel and the average. And the last properties we have to know are properties of isosceles trapezoids. Isosceles means two congruent legs. So the first property we need to write down is that legs are congruent. So not only are the bases parallel, but the legs are the same length. The nice thing that happens then is this thing takes on some symmetry that other trapezoids don't have. If you imagine a fold through the middle of the two bases, the left half and the right half of that fold are going to match if you actually complete the fold. So we have a line of symmetry right down the middle. Because we have a line of symmetry, we get some special properties. The first of which is that base angles are congruent. So along any one base, you get two of the same angles. So if the top left-hand corner was 60 degrees, then the top right-hand corner is its mirror image. It must also be 60 degrees. So two angles at that top base have to be the same. We also know that the angles along the leg add up to 180. So 180 minus 60 would give us 120 for the bottom left-hand corner. And then its mirror image in the bottom right-hand corner is also 120 degrees. So if you know one angle, you can find all the rest. Only if it's isosceles. If it isn't isosceles, you have to know at least one angle at each leg to find the other two angles. There's one more property. We'll have to draw an extra little bit in here. If we draw in the diagonals, and this kind of goes back to the symmetry issue, from the top left to the bottom right corner, and from the top right to the bottom left corner, those end up being the same length. They even look like they're the same length. If we fold the figure in half, the long pieces of the diagonals will overlap each other. Those are going to be congruent. And then these short pieces of the diagonals down here, those are going to be two equal short pieces. So they don't cut each other in half, but the short pieces are equal and the long pieces are equal. So we're going to jot down that diagonals are congruent. And then the parts are congruent. There's not an easy way really to list that, but if you take a close look at the picture, it should be apparent that you have some equal pieces. You have an isosceles triangle at the top of this picture and an isosceles triangle at the bottom of the picture. Left and right, they can be any old kind of triangle. Those are typically scalene. Alright, so now that we've actually got all the properties written down, let's look at some sample problems where we apply those. So flip the page. So these are the sorts of things you might run into in your homework or on standardized tests. Find the measures of the number of angles of each. Directions are important because they tell us things. Isosceles trapezoid. Well, they actually have marked the parallel sides. They've marked the congruent legs. So even without the instructions on this one, we could have known it was an isosceles trapezoid, which means the base angles are going to be equal. So if angle O is 135, angle N is the corresponding base angle, so 3 must also be 135 degrees. To find angle 1 and angle 2, we need the property that says that angles along a base have to be supplementary. So on the left side, 180 minus 135 is 45, so angle 1 is 45 degrees. Angle 2 is its mirror image, so angle 2 is also 45 degrees. Second example you have to be a little more careful of because it's turned around so that the bases are on the left and right instead of the top and the bottom. If you have trouble looking at it in that perspective, all you have to do is turn your paper around. When you turn your paper around, the bases are on the top and the bottom, and you do it just like the previous problem. Base angles are congruent, so if angle T is 85 and Q is the corresponding base angle, then angle 1 at vertex Q has to be 85 degrees. To find R and S, or angles 2 and 3, we'd have to subtract 85 from 180. 180 minus 85 is 95. So angle 1 is 95 degrees. Angle 3 is 95 degrees. And we won't worry about the fact that when you turn your paper back around, those numbers are sideways. It doesn't matter. As long as you can find the angle measures, we're in good shape. Okay, now throw in a little algebra. Can't ever get by without that. Find the values of the variable or variables in each isosceles trapezoid. Okay, on the left, it might help to turn it around. Put the base on the bottom, a base on the bottom, doesn't really matter which one. This is the most comfortable perspective for most students. Two legs are equal. We know nothing about the base. Nothing at all about the base. Do not try to use it. Ignore it. But we know these two legs have to be equal to each other. They're even marked, so we're going to make an equation that says that 3x minus 3 is equal to x plus 5. Probably need to turn my paper around for this one. So 3x minus 3 equals x plus 5. Subtract x from each side, we get 2x minus 3 equals 5. Add 3, we get 2x equals 8. Divide by 2, x equals 4. That's all we had to do on this problem. We could do a quick substitution just to check it. If we substitute a 4 in on the bottom side, we get 4 plus 5 is 9. We substitute a 4 in at the top, we get 3 times 4 is 12. 12 minus 3 is 9. Those should both be equal. They both are 9, so we did fine. If we wanted to find this base, we could do 4 minus 1 is 3. The base is a different length. It doesn't have to be the same as the legs. Nothing wrong with that. Alright, next problem has a little algebra worked in, but this time we're dealing with angles. So this is isosceles. The top two angles are going to be the same. The bottom two angles are going to be the same. Well, we don't know the bottom right, so that's not useful. The top angles, one has an x in it, one has a y. That's not helpful either. We can only solve for one variable at a time. So what we need to do is focus on the two with x's in them, and those are along the same leg. Those two have to add up to 180. So we're going to say that 6x plus 20, first angle, added to the second angle, 4x, equals 180. We're not going to use that third angle at all just yet. Combine like terms. 6x plus 4x is 10x. Bring down plus 20 equals 180. Subtract 20 from each side. We get 10x equals 160. Divide by 10. We get x equals 16. We're almost finished. We were told to find the values of the variables. We still have to figure out y. Well, to get y, we're going to need to figure out what that top angle is. So we substitute that 16 back in up at the top. So 6 times 16 plus 20. 6 times 16 is 96. 96 plus 20 is 116. So if the top left-hand angle is 116, then the top right-hand angle must also be 116. That's what's labeled y, so we know that y is equal to 116. Alright, we're on the home stretch, just a couple more. Okay, we have a mid-segment problem here. XY is a mid-segment of trapezoid. Might help if you turn it around this way and look at it. I know that this is a mid-segment XY because I have midpoint on the left, two congruent parts, and a midpoint on the right. Y is in the middle because of the two congruent parts. To find the length of XY, I need to average the 5 and the 2.5. How do I average? Add them up and divide by 2. Alright, 5 plus 2.5 is 7.5. Divide that by 2. 7.5 divided by 2 is 3.75. So 3.75 is the measure of the midsegment. We don't know units, so we'll just not bother to put any on there. And finally, we get a kite problem. There's not a lot of those floating around. For which value of x is this figure a kite? Okay. Well, it's turned around so that, well, let's see. If GT is 17 and TO is 21, those are two different lengths. That means there's a short side and a long side there. Maybe I need to turn it around to look at it this way. Okay. Short side here of 17. GL should be the same. It needs to be 17. If TO is 21, then we know that LO is also 21. So we have to kind of turn around and look at it from the right perspective. If I want to find X, then I either need to set 4x plus 1 equal to 17 or 6x minus 3 equal to 21. Don't try to set 4x plus 1 equal to 6x minus 3. Those are not equal parts. So let's just pick one. Let's take this one over here. 4x plus 1 equals 17. If we subtract 1, we get 4x equals 16. And divide by 4, we get x equals 4. Let's check it. Put a 4 back in here for LO. 6 times 4 is 24, minus 3 is 21. That one works. So x equals 4 is the correct measure. Alright, one more slide. We're almost done. Another trapezoid with a mid-segment given. This is a typical sort of higher level ACT question. I'm going to have to use some algebra. Might help if we turn it around and look at it this way. The length of the midsegment is the average of the two bases. Oh, this one looks way harder because we actually have to add and divide by 2. Okay, let's take some space out here. Let's add the two bases, x plus 3 plus 4x plus 1. Have to divide that by 2, and that should equal 22. So this left side, we're just averaging the bases. To average, you add up, divide by 2. It looks more complicated, but you treat it the same way you do the numerical problems. The setup is still the same. It just looks like it's going to be hard to solve, but it's really not as bad as it looks. The first thing I'm going to do is multiply both sides by 2, because if I multiply both sides by 2, it'll cancel the 2 in that denominator, and I can get rid of that fraction. Multiply the other side by 2, and I'm going to get x plus 3 plus 4x plus 1 equals 44, and it already looks better. Now, some of you clever folks can go ahead and add your like terms in this same step if you want to. I'm going to do that in a separate step since I didn't do it before. X plus 4x is 5x. 3 plus 1 is 4. Bring down your equals 44. Subtract 4, we get 5x equals 40. And then divide by 5, we get x equals 8. Which is the answer to part A. What's the value of x? It's 8. Now I have to find xy. So put 8 back in for x and xy. So 4 times 8 plus 1 is 32 plus 1, which is 33. Okay, 33. And then WZ, substitute an 8 in for that x. We get 8 plus 3, which is 11. So WZ is 11. Is 22 halfway between 11 and 33? Yes, it is. So all of our work is correct. This is the most complicated thing we have. Getting this setup done is the key to success. And 2 quick cut problems to finish this up. Okay, this one's a little bit of a challenge. I know that if I draw in a diagonal here, that's a line of symmetry. So 1 and 2, they're mirror images of each other. They're going to be the same. Oh, angles of a quadrilateral always add up to 360. That might be a good place to start. We have 360 degrees total. 101 plus 48 is 149. So if I take out the 149 that I already know, that's going to leave 211 degrees for the other 2 angles combined. And they're equal. So if I divide the 211 in half, that'll give me angle 1 and angle 2. So 211 divided by 2 is 105.5. So angle 1 is 105.5 degrees. Yes, you can have a half degree. Nothing wrong with that. And angle 2 is 105.5 degrees. Last one, we have some diagonals drawn in. That's going to hopefully speed up the process a little bit. I'm going to just start drawing in some things that I know. First of all, around the middle here we have a bunch of 90-degree angles. That's going to be helpful. I have a 27-degree angle in the top right-hand corner. That means the one under is also 27. Those are equal angles. Look just at this top right triangle. That triangle has 180 degrees in it. Alright, 180 minus 90 and 27 make 117. That leaves 63 degrees for angle 2. So angle 2 is 63. Angle 3 down here is its mirror image across this horizontal diagonal. So angle 3 is also 63 degrees. Angle 1 is the right angle that's already marked. So angle 1 is 90 degrees. The key to these is knowing that your adjacent angles by your pairs of congruent sides are equal, and that there's 180 degrees in each triangle and right angles in the middle. You can figure out everything else that's going on that you need to know. You have a worksheet, 6-6 practice, that you need to work on now. If you finish it with some time to spare and you still have some work to do on yesterday's worksheet, today would be a good time to finish that up. We will do some extra practice from all the sections put together tomorrow and be getting ready for the test over Unit 6 on Thursday. I strongly suggest you start studying now and not wait till the last minute to try to cram things in on Wednesday night or Thursday morning. I will see you tomorrow.